All right, good morning, everyone. We're going to go ahead and get started now. I think there's still a line of some people coming in, but we'll get started so we stay on schedule here. Today's talk in this room is going to be data science with Spark. We've got a couple of slides that we're going to go through on data frames and machine learning, the MLlib libraries, and a lot of labs as well. So I'll just give you a quick introduction to myself. I'm John Bates. Did a lot of work with automating systems and analyzing data in finance to trade municipal bonds. And since then, I've been more focused on just a pure data science track and working with some companies doing consulting and including like click-through rate prediction, things like that. I helped teach as an assistant instructor for the MOOC, the Scalable Machine Learning. So if anyone took that through edX, there are quite a few labs in there, and I did a lot of work on making those labs as clean as possible. So we'll go ahead and get started here. So the first thing we're going to introduce is data frames, and data frames are really kind of the direction in which Spark is really moving here. And with machine learning, you'll see that the ML pipelines and all the ML estimators and transformers are using the data frames underneath the hood. So we'll go through an overview of MLlib and ML. And then there's a series of labs that we can work through. And we'll use these to go into more detail on just how data frames and how you call the APIs and really just to solidify the understanding. There'll be sections that have to-dos that you need to fill in and then some tests. And we'll walk through the code. So it'll be pretty heavy on notebooks and going through the actual code and explaining how everything fits together. So I want everyone to come out of here with definitely an understanding of the APIs, how you reference where there's additional information. So like, okay, I can go to the ML programming guide, or I can go to the actual API itself, or I can just look at the source code to get more information. And these are all resources that I want you to be familiar with so that you can continue your learning beyond this training and cover the features that we're not able to cover in just this one day. So here's just an idea of some of the labs we have. We won't be able to get to all of these, but I'll actually give you guys an overview of what's in all of them, and they're all within your personal folders. So you should be able to see these and then go ahead and either download them, or you'll have access for a few weeks after this training ends to this shard. So that'll allow you to actually go ahead and continue looking at these labs. Okay, besides this, we're going to cover user-defined functions, and that's going to be including the MLlib data types. And so there are a couple of quirks about using the MLlib data types within UDFs. Some plotting with matplotlib. You won't have to actually write any code for that, but there's some demonstrations. And then training and testing, how would you actually do your splits? How would you do sampling and stratified sampling, and some other topics as well. Okay, let's do a quick before we go into the data frame section. If I could just see who here has actually used Spark before. So if you go ahead and raise your hands. All right, so that's great. Excellent. And then data frames, who's familiar with Spark data frames? Okay, great. And then within the machine learning, the ML library, who has used pipelines and cross-validation within that? Okay, cool, just a few. Great. All right. And then I guess with languages too, let's go through that real quick. What's your preference? If we were to cover, saying there's three main languages, you've got Python, Scala, and R. So we'll start with Python first. If that's your preference for using in notebooks, go ahead and raise your hand. Okay. And then if Scala is your preference, great. And how about R? Okay, great. Well, the labs will be in both Scala and Python. Unfortunately, they're not ported to R at this point, but hopefully you guys can manage. Definitely the DataFrame API is a lot like SQL, so those familiar with SQL will have a lot of comfort around the way in which we're doing things there. Okay, so data frames. First off, what are data frames? Well, a data frame is really you could think of it as a table, and within that you have a name for your actual columns, and then you have a schema associated with that as well. And then you can just store within rows your various bits of information. So in this example, we have a name, age, and address column. And then the name is a string. The age here, I believe, is a big int. And the address, it actually looks like an array. But it's not the case here. It's actually a nested structure where this is another structure itself. And we have two parts to it, one being the city and then the country. So we can see that where we actually look at the schema. So every data frame has a schema associated, just like you'd have with a table in SQL. And here you actually have the names, and you can see address has this structure to it, so it's a nested structure within our data frame. And all of the fields here currently are set to allow null. But this is a nice way you can actually print this out just with this format right in Spark. So how would we go ahead and create this data frame? So we're using name tuple here, which within Python is nice from the aspect that it keeps everything in order. So we could just go ahead and create a person name tuple, which is kind of like a case class in Scala, or go with a address one as well. And then when we create a person, I'm creating 3 different rows here. The first one just being Bob, who's 35, and we give an address as well. And we can do that 3 times here, and just use a SQL context to go ahead and create the data frame, passing in the 3 rows in an array. And then we could display it or do a show to just see what was actually in there. OK, so here's a couple examples of how we would actually go about using a data frame. So let's say from this table that we just created, we wanted to select the people that are older than 30. Well, here we can use people.where, and then we give it a column and say just greater than 30, and that'll return those results. So it's pretty straightforward. If you're comfortable with data frames from Pandas or from R, you'll see a lot of similarities with the way in which this API has been constructed. And it really much follows from the SQL world to the sort of functionality that is built into here. Now, people itself is the data frame. Where is going to be a method on the data frame. And then people, where I have the brackets here, I'm indexing age, which actually returns the column, age itself. There's several different ways to go about getting a column out. But that object that's coming back here is a column itself. And since it's a column, when I use the greater than symbol, it's actually able to compare to the column itself. So the comparison will occur across the set of rows, and that'll be compared to 30. And that'll return us another data frame. So the data frames, too, when you run an operation on one, you get back another data frame. With Spark, everything is considered immutable, so we're not really changing state. We're actually returning ourselves a new data frame, which is the same way that RDDs would work. You should always think about them as being a new version on top of the old one, and you're not trying to actually mutate any of the actual state within that object itself. So how about when we get people from the United States? So here we can actually use the nested structure, and with addresses with dot notation country, go ahead and pull out USA and compare that and do a select. So just like your normal SQL statements, you would have a select clause. And here we're just saying, if I didn't use select, I'd get back all of the fields. But now I'm just pulling out the name field. So select is an operation that's occurring on the data frame that's been returned by doing the where. And then this is actually not doing any execution until I go ahead and ask for results back. So all these operations are lazy. Now let's say we wanted the average age. Here, we could go ahead and use functions that are built into a helpful library. So this is the PySpark. It's SQL.functions. There's also functions within Scala. And that will allow us to go ahead, and we're pulling it in as an alias for just func so we can keep it shorter in the code. But what we do is we tell the data frame to aggregate itself. And then that allows, it's a group by with essentially no fields. So it preps the data frame in order to be able to use these aggregate functions. And in this case, average is an aggregate function, which will calculate the average over the column that we pass in. So we pass in a column of age, and then we're able to, that goes into the average function, and then I'll go ahead and calculate out what the average age is for our entire data frame. So I want to jump into there's 2 links here for the Python API and the Scala API. I'll just pull these up real quick. We'll start with the Python API. It's coming up. Let's see. Is that, can people see that? Just go ahead and raise your hand if that's clear enough. OK, great. It seems like everyone can. All right. So within the API, the major things you're going to want to look at the most are going to be data frame objects themselves, which is where all the operations that you can do on your data frame are going to live. A column. So within the data frame is made up of columns. And then there's a bunch of operations on columns that are very useful. Besides those two, the next, I'd say, most important is this functions module. And within functions, you get a lot of stuff where you can pass in, usually you pass in a column to it, and it'll return another column. So once you get that column back, you could go look at the column reference and say, OK, what can I do now that I have a column again? So an example of that would be, if I looked at the column, you see this alias. So I've gone out, in this example, I've selected out age, and then I've given it a different name. So selecting age gives me a column. Alias is an operation on a column. So I've just gone and renamed it to age 2. So this is definitely a great resource. And you'll find that there's just a ton of functions in here that are very useful. OK, so why would we use data frames? For one, it's a greater accessibility to people that have a background in R or in Pandas. And there's a familiarity of people with a SQL syntax. It's a lot more clear than doing some of the RDD operations. Although once you get comfortable with the RDDs, it can be a little bit difficult to say, oh, I want to go switch back to data frames. Now, it's declarative rather than imperative. And what this means is with RDDs, you go ahead and you actually say every step that you want to do. But data frames, you go ahead and you say, OK, well, this is what I want to get out of this from a more logical standpoint. I want to group this data, and I want to pull out these fields. And I can keep composing on top of that. And what that really allows is us to optimize under the hood what's going on. And that's the Catalyst optimizer. So now at the end of my, I've done a bunch of operations on a data frame. And then I say, OK, select out just this column. I may be able to say, let's reorder what's gone on here and push that down all the way to even the layer where I'm pulling the data out. So this could be a database. And I push this predicate all the way back down into the database. I never have to retrieve those columns. And this can happen much later, because the execution doesn't happen until we actually call an action. OK, so some of the transformations and actions, just as examples here, you've got things like filter. Filter actually is going to look the same as where within a data frame, so those two are really aliases to each other. Select, drop, join, kind of standard operations you would do in SQL. And then actions, these will actually go ahead and cause the data frame to go ahead and execute, and actually tasks to run out in your executors in Spark. And things are like count, collect, show, take. And here I'm just saying, transformations, nothing occurs, really just a plan happens. And then when we go ahead and execute an action like take 1 to get back to the first row, then we actually cause a whole plan to execute. And these RDDs will be used underneath the hood, and then results will be returned to our driver. So just for a little terminology for those who aren't familiar, with Spark, we'll have a driver, and then we'll have executors, which are living on the workers. And the workers are going to be sort of the nodes in your cluster that are doing most of the work. But when you go ahead and you actually run an execution here, you say, OK, let's count something. It'll create the plan and the driver, and then send out that plan and the code that's required to run it to the executors. And then they'll actually run and then come back with results, which will be sent back to that driver. All right, so what does query execution really mean? Well, first off, it's typically going to be a distributed read, and that's coming from, say, a Parquet file, a table, a whole myriad of possible data sources. So it's got to go ahead and get that data in. Or maybe even it's something where we've cached this into memory, and we can pull it directly from the memory. After that, we're usually using RDD transformations under the hood, and so this is going to follow from those familiar with the RDD, the existing RDD API. There's actually just a few things that are used under the hood to call. I mean, big one is like map partitions, zip partitions, and then also doing shuffles. And then once you have calculated these results, you want to get something back to the driver so you can continue your analysis. And that's where you deliver back those results. So how do data frames compare to RDDs? And that if you've seen some of the blog posts and things, you've probably seen this graph. And it's really, they can be a lot faster, and there's several reasons for that. It's a little bit misleading, I think, this graph, if you say RDDs in Scala are quite a bit slower than data frames, because they are actually, it's still RDDs in Scala in the end. You're still using Spark Core and using these existing, it's Scala code that's running with RDDs. But it's highly optimized. And if you've done something naively with an RDD API, if you go ahead and you use data frames, it's likely that there's a lot of optimization that's gone into that, so it's probably going to run a lot faster. And then Python here is really just a question of dealing with the Python interpreted language and having to create separate processes that run, and then the information has to be serialized, passed back and forth between the JVM and with Python, so that definitely slows things down. Now also, the data frames in Python are going to run just as fast as Scala as long as you use the existing functions and libraries and call directly on DataFrame or call on a column. But if you go ahead and create your own user-defined function in Python, that still has to execute on an executor using a Python process. So it's likely that that's going to execute more slowly than that same user-defined function that's generated in Scala. OK. So we're going to go ahead and move on to a couple of the labs here. We'll do some hands-on practice with data frames, and I'll walk through some of the code there. So if everyone, I know you all have logins based on, you should have a username and a password that was given to you with your placards. And if you haven't been able to get into the Databricks logging into your shard, definitely raise your hand and get the attention of a TA, because we'll be going through those. It'll be nice if you can follow along. The first one is really just going to be an overview of how the ETL process went. And then from there, we'll actually do some exploratory data analysis, and that'll be using the data frames. So definitely try and get attention of a TA if you're having problems getting into the shards here. So. All right. Once again, how's the size for everyone on this? If you could just raise your hand if you can see this OK? Yeah. OK. OK, so everyone should be pulling up a browser where your URL looks something like this. There's a range of 6 different shards from DS01 to DS06. So if you should be logged into your own shard here. And then I'll just point out a couple of features on how you can navigate around. If you see this 3 bars on the top left, that's actually basically a navigation system to get around the system. And then within Workspace, you should see your name or the user account that you're using. And you can go down and find within there should actually be a labs folder. So within labs, the first one we're actually going to go through is this wiki-etl. Now, each of the labs has this first one is actually just going to have Python. And within that, you'll find there's just there's 2 notebooks there. There's an answers, and there's also a student notebook. Now, you should typically use the student notebooks. The answers, there's actually no exercises in this first lab. But to the extent that you have exercises to do, there will be also an answers, which contains the answers to those exercises. So if you need a reference and you're getting stuck on something, definitely go back and check that out. All right, so for this first one, we'll just pull up the ETL. OK, so the first example here we're going to do for the lab, and the next lab that follows this uses Wikipedia data. And it's made available through a system of, there's a dumps on dumps.wikipedia, which actually has various versions from about every month. It's a full text capture of what the Wikipedia articles are. So I'm assuming people are familiar with Wikipedia, but just in case, we can go ahead and pull up. It's an encyclopedia. We'll be using the English version, just a series of articles, and the article text will be captured within this download that we do. So that makes it really a text processing exploration, which is kind of interesting how we could use data frames to do that. All right. So let's go to ETL. So just to give a little background, this notebook I've created and put here really because this was a process that I used to get the data and then make it into a form usable in the Parquet format to go ahead and do analysis with Spark. So this is really so you can go and recreate this analysis if you want to do it offline or you weren't starting from the Parquet files that we're going to start with for the other stuff. So we'll move through this pretty quickly, and I'll just talk about a couple of aspects about it that are interesting. The download from Wikipedia is in an XML format. And there's a problem with this type of format because you have to go through and parse each of the tags, but there's one huge tag that embeds the rest of the other tags. So it's not easy to parallelize something like this. So it's definitely something you should think about when designing a process where you're pulling data into your system. If you can distribute that data ahead of time in a way that you can have multiple files that are broken up in a logical way, it makes reading that data in much easier. So what we did is we actually just took this XML file and parsed it at once into JSON files, where the JSON files have a single line that corresponds to an article. And it's very easy to read that JSON in and then convert it into a Parquet format using Spark. And this entire data set is around 50 gigs once you uncompress. So if we just go take a look at the code here, this is an example. OK, so when people are looking at the notebooks here, you'll see there's a detached state on the left. And you want to find your cluster. There should be a cluster corresponding to your name. You can go ahead and attach to that. You also do that with each notebook that we use. Yeah. That good? All right, so once we've attached, then we can actually go ahead and run code samples. This is just showing the structure of XML here. So there's actually a series of pages within the Wikipedia data, and you'll see there's various fields like the title or an ID, revision that was done, who actually made that revision to the article, and then text. In this case, we're dealing with a redirect, so this is just going to send us to another part of Wikipedia. But you'll see the full text for an article in here for articles that are complete. So what we did is we took, just using a Python library, did XML parsing of this to go ahead and create the JSON objects and bring them into Parquet. As you can see, all that I needed to do once I had a JSON file here was read it in using a SQL context, and then I could write it out using a Parquet file. So really straightforward when using Spark. And this is all handled in a parallel fashion and is actually quite fast. When you create the Parquet file, it'll write everything out. So like this actually was done using something like 1,300 partitions. So it creates 1,300 different parts files for the Parquet. And you can find some details about the Parquet file format on this link that's provided right here. It's really columnar storage, which is great for doing things like this where we're going to be working with data frames. We're already dealing with a column structure. So we have a schema for each of these things. And now that, let's say this particular column is an integer or it's a string, it's going to be a lot easier to go ahead and compress that down. And then if we need to do a predicate pushdown where we say, I only want the first column, all I need to do is Parquet can actually go ahead and say, OK, forget all these other ones. I don't need to actually touch that data and load that in. So it's going to be a lot more efficient than saying just load from text or try and do your processing after you've already pulled in all this data and saturated your network. So to create some data sets for the classes, I also just used a sampling procedure here to create smaller sizes, and I used coalesce just to create less partitions instead of creating 1,300 different files. After doing this, I'll create 24 files. So this is just an example that you can use this if you want to go ahead and recreate this analysis locally. We don't need to actually run anything in this notebook. All right, so the next one we want to look at is where we're actually going to do our exploratory data analysis. And that you'll find under your labs folder, Wiki EDA. Now here we'll have two options. There's Python and Scala. And you'll find for most of the labs, you're going to have a Python and a Scala option. Now, we go into Python. So I'm going to do the demos mostly in Python, but feel free to choose whichever one you like. And then you'll see that there are answers, again, and a student version. So I would recommend you take the student version. If you're not very comfortable with coding, you can go through answers and just follow along. But if you'd like, there are going to be some exercises throughout. And in this one, particularly at the end, there's several exercises. So if you want to try those, definitely take the student version. Always you can reference side by side the other version with the answers. Or you could always pull up both Scala and Python and see how the two differ. You'll find the APIs are actually pretty similar between the two. You just have to deal with types a lot more with Scala. OK. So the idea here is to get comfortable with data frames and some of the operations that we can use on data frames when working with a data set like the Wikipedia data set. So first off, we're going to be loading the data, but it's important to understand what APIs are available and what guides are out there to get more information about how to do these kind of operations. So you'll see links here to the Python and Scala APIs, and then also the Spark SQL data frame guide. So let's just pull up the Spark SQL data frame guide. All right, great. So you can see there's just a lot of information that's provided here with all links to different things that you can do. This is definitely higher level. You'll probably want to go for specific operations. You'll want to go into the actual APIs that you find under API docs. So if we went to API docs and said, OK, I want to look at the Python API, here we're dealing with SQL. Data frames fall within the SQL module. So I can just pull this up, and then I have, again, all the different types that I might have to do operations on. So let's say I wanted to just figure out, like, how do I get some column out of a data frame? So I could go into this data frame class and start looking around. You can just scroll down and see the different classes that are there. Or you can also, I usually just typically go ahead and do a search. So let's say we want to say, OK, are there any examples with select? And you can just see right here, this is an example where someone's doing the join data frame. They're selecting out a column, a couple of different columns, actually 3 columns here, and then just collecting them back to the driver to view them. And it's a small data frame, so there's only 2 rows. So we're getting back Alice and Bob. It's very straightforward here. OK, so then from there, we'll go ahead and we'll start by loading the small sample that was generated in the ETL process. So to run a cell within the Databricks notebook, you use Shift-Enter. So once you're within the cell, you can hit Shift-Enter, and that'll go ahead and execute our cell. And we'll see this progress bar on the bottom for what's going on. You can also click on the little arrow that's right next to it and view the various jobs that were launched to complete the process. There'll be additional details there, including going out to the user interface that's provided, and you can see a little more information about just exactly what's happening. We'll go into this in some detail later, but one of the most useful things is to see a visualization of the directed acyclic graph that's generated. So what's actually happening underneath the hood. There's a parallelize operation and a map partitions operation. So this can be useful for sort of seeing what's actually being created underneath with the data frames API and what's being executed. If things are running slowly, you can see what parts are running slowly and get a better idea about what's really going on. And there's a couple other tabs across here we won't worry about at this point, but might come back to them later. All right, so first thing we did here is we loaded in our Parquet file, just giving it a directory. This is actually loading from AWS in an S3 bucket. And then calling cache to just store it in memory to make our subsequent operations faster. You'll see I do use cache fairly often. You typically probably wouldn't use it as much as you'll see in some of these examples, because what we're doing here is we're displaying, we're moving one step at a time. And every time we do this, we can keep things in memory so that the process is going to be faster. Typically, you would actually put together a bunch of transformations and then run your operation at the end, so you wouldn't be needing to cache all the intermediate things that are going on or be worried about doing the data load so many times. But here, because of the way we're doing this in a more interactive way, we'll do caching pretty frequently. OK. And that caching just will store it in memory. That's the default for it. It'll go ahead and, if possible to fit within memory, it'll store it on the executors so it's available for future iterations on that data set. All right, so let's go ahead and take a look at this data frame that we've created. And we go in here to this cell again and use a Shift-Enter. We can see this data frame comes out with the various columns that we've saved. And this was based on what we did in our ETL process. So we've got a last contributor, a redirect title, a text string, the timestamp, and then also a title. And the type for this, for Python, you're going to see it's the SQL DataFrame.DataFrame. So this is a DataFrame object that we are working with. Now, how would we find out what's actually the official schema that's being used here by Spark? Now, the first operation is to use dfsmall.schema, and that's going to just give us a more type-focused list. So this is a structure type, and that's how you actually would go ahead and specify exactly what schema you wanted to use. And a structure type contains fields. And those fields, one of those fields could actually be another structure type. And that's where we get like a nested structure with the example where we had an address, and that was part of a person. So here we have several different structured fields. It's just as an array of fields. The example would be the last contributor username. This is of a string type. So data frames need to know the type, and that allows for a lot of optimizations with our schemas. It allows for for the compression to be good for one thing, but then also it allows bytecode generation when things like expressions are being done, and you can actually keep things in a very optimal fashion. So the schema that you specify here is really a big differentiator between RDDs and data frames, and that allows for these optimizations, but it does restrict what you can do a little bit. So here we can see a nicer printing using print schema, and this is where we have the root and then all of the fields that fall underneath it. So you'd see a nested structure if it were to occur here as well. And you can just see the types that are being used within SQL, sort of the SQL libraries. String, 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 string. They're actually all string for this one, so it's not as exciting, but we'll see we can create different types from like a timestamp using functions. So within Python, a couple things you can do to get more information is to use help. And so once you've imported this field, like, okay, a structured field, how does this class actually work? So let's go ahead and call help on it, and we'll see some information about the parameters that it does take. These include name, the data type, which we saw, like, so string type, and whether or not you can actually set these things to be null. So like from the SQL world and the database world, is this field allowed to be null within this table? And then there's also metadata. And metadata, we'll see later, is actually used within ML to store some information about just what these objects are. And that can be used to not have to process the entire entire set of rows, the entire data frame to figure out something. We can store that information ahead of time. So let's go ahead and move on through here. All right, so then we could go ahead and create our own schema and specify that out with using the structured types. So here we're going to say, okay, let's pretend we have some data about Wikipedia, and it's about what users did with editing, and how often were articles edited, what was the title of the article, and then was one of these edits redacted because like there was something wrong with the edit or it didn't follow the regular process that people expect. So we can create that using these structured fields and passing in the types, and then this first one I'm actually going to make a change and say, okay, this can't be nullable. And then I'll give it some metadata as well. So the metadata is really more of the developer API level, so you shouldn't really typically be needing to use this unless you're writing, say, your own estimators, transformers, things within the ML library that need to operate on this, or custom functions that would look at this metadata for some reason. But it will be used behind the scenes, so it's nice to know that it does exist there. So we can go ahead and create a data frame using the row object. So row just corresponds to a row within your data frame. And we can specify the various fields that we need here. And then what's going to happen is, since we've specified what the schema is, we can use the SQL context, create data frame, pass in our data, and scparallelize will create us an RDD. So this is a function that takes in an RDD and then a structured type that corresponds to the schema, and we'll create a data frame that we can use display. Now display is this is a Databricks specific functionality. We could also call example df.show, and that would give us a less pretty printout of what this is, but that's built right into Apache Spark. Let's go ahead and take a look at that. As we can see our titles, the number of edits, and whether or not it was redacted. Okay, so let's make sure that schema came through just fine. So again, Shift Enter. Oops. And we can see the structure looks like what we specified Here we have title, which is string, number of edits is a long, redacted is a Boolean. So this is good. But we didn't see anything about metadata here. And that's something that we want to, how could I capture the metadata and see what was going on behind the scenes a little bit? So let's go ahead and take a look at that. We can actually access the schema. And then within the schema, there's a list of fields. So that's just accessed using fields. And then that's an array. So I want to say, look at the first field within it. And that's going to correspond to our title. And then the second field is going to correspond to number of edits. So let's see if either of those have any metadata associated with them. And this first one, it does have actually the language English is specified. So this is something where we could actually, maybe there's a library that someone builds or we build, and what it does is it translates a column from one language to another. It could read in this metadata and say, oh, the column's already in English, and I want to convert it to someone specified that I want it in German. Now I can just go ahead and make that translation. Otherwise, I'd probably have to read in that entire set and try and infer what that language was first. So this allows us to save some processing, and we'll see it used in ML for dealing with different types. Like, is this a nominal type, or is this some continuous type of variable? So it's useful for that type of thing. OK, so what does a row within Wikipedia actually look like? We'll go ahead and run this cell. So this is not super easy to read, but you can see that a row consists of various fields, like the last contributor username, and then we see the string that's associated with that, and then a redirect title. In this case, redirect title is going to be null or none for a lot of the observations, but it just means that this is not a redirect. So we can go ahead and later on we'll actually see how we pull out which ones are redirects, which ones are not, so we can filter for those, because that's sort of, the text for those just sends you to another article, so it's not that informative. Then we have the actual text for the article itself, and it uses some of this formatting that's specific to the format that Wikipedia uses with the brackets and whatnot. So we'll have to deal with that later as well. So we'll go ahead and scroll down through this. And then it's hard to read everything that's going on there. So if we just wanted to know what the column names were, we can use .columns. And this will give us just a nice list, and that'll be a reference that we can use later for select statements and things like that. OK, so now text, that was also a really big field that had the article text. So let's say we want to run this operation drop to remove that. This is going to return back another data frame, and we can just take the first element of that data frame and display that. So this will really be the first row, and that's going to be the first row without text. So this one here, we can see, oh, it's a lot easier to read. We have a title, we've got a timestamp, redirect title, so I can start to look at it and just see what's going on a little bit better. All right. Now we could also just use print here to go ahead and print out using the new lines, so you get a little bit of an idea of what it might look like more so on Wikipedia as well. Now part of the ETL process was to parse this XML. And when we parse the XML, we can get errors because the tags were not actually well formed. So in this example, I've gone ahead and with the ETL process, whenever there was an error, I just say, let's call the title parse error so we can look at this later and maybe figure out what was going on. Or we could just go ahead and say ignore those types of fields wherever that occurs. So we'll go ahead and run this. We'll run a count on it. We've run a filter. So filter is just another data frame operation, which was equivalent to where, right? So both of those are the same thing. And we're doing something different here, though. We're importing call from functions. So functions has a lot of very useful helper functions that let you work on a column and convert it to another column that the data frame API can work with. And so this will, using text passed into it, will give us call back. So this is a column of title. So it's just one way to reference it. I think in the earlier example, we saw bracket notation. You can also use a dot notation. But this is consistent between both Scala and Python. You can use it in both. And it's just a nice shortcut because it's only 3 letters. If you had a long data frame, this will save you some typing. So we'll just see how many errors we did have in this data set. It was only 12. It's a small percentage of the overall data set. So it's not too concerning if we want to go ahead and drop this later on. But how would we, so this is an example of how we'd actually go ahead and do the selection using the bracket notation or just a dot notation as well. I'll stay there for a second just so people can see. Data frame here, operation on the data frames. This is a transformation. And then this is the data frame, but we're referencing a column, so this will return back a column object. That column object we can call using the double equals to just do a comparison to see if it's the string parse error. Within Scala, you'll see you'll need to use a triple equals because of the way the operator overloading works. And then at the end, we get a data frame back that we call count on just to see how many elements are in it. All right. So now, let's say we wanted to just take an existing title and rename that title. This is where we can use alias. So here we're doing a select statement, which operates in the data frame. Column of title, this is getting us a column, so it's the title column. And now that we have this title column, we can go ahead and do an alias on it called bad title. And we'll show 3 of these just to see what that looks like. Now, the interesting thing here is we can also do a select statement where we just pass in title. But if I did that, I can't actually go ahead and say, rename this to bad title in the same step, because that's just a string. And if I were to operate with alias on the string, it's not implemented by string. So by using call, that gives me back an actual column object that does implement alias. So that allows me to rename it. So that's one of the useful things for using call. All right, let's see what does one of these errors actually look like. So we can take the text for the first error, and the bracket notation on the end where it's a 0 here is actually just we've pulled a row down. And with that row, we're going to get the first element of it. This row only has text within it, so it has one element, and we're going to get that first one out. So if we take a look at the text that we get here, we'll go ahead and see that it's very much XML, but there's a problem toward the end. If we scroll all the way down to the end of it, you can actually see, so there's a nice scroll bar over here, so you can just go ahead and slide that down. At the end here, you'll see that text is actually malformed. There's not a I guess a less than sign on this text. So XML wasn't able to parse it for that reason. So now, this also looks a little bit like a draft article, so it's probably not bad to just go ahead and drop these things. But we could work on actually replacing this text as well and say, OK, we still want to capture these things or do more investigation into them. But that's what's actually going on. All right, so now there's this other column, which is your redirect title. That's one I mentioned before. These just redirects when you click on the link, it'll send you to another link within Wikipedia. So we want to go ahead and take that column using select. So I'm going to select column redirect title. What I want to do is find the ones that are, so if I use is not null, this is going to tell me a Boolean value for whether or not this column is null. So now I've converted this from just being a string type that can be null to a true false. And then I'll give it an alias. Does this have a redirect? So now I've renamed the column, doing that right here. And then we can use a group by, which will go ahead and aggregate based on this column we've created that has these 2 different values. So now it's going to group it into the true and the false values. And just go ahead and call count, because group by now we've got back a grouped object. And if we looked at the SQL, so this is grouped data that comes back. If we actually look at the API, you'll see there's a grouped data object. So whenever you call a group by, it returns a grouped data. And if you call, there's also this ag function. If you just call that, it'll call group by effectively first automatically for you. So it's sort of an alias for group by and then ag. So within the group data, you can see there is this aggregate. There's a couple other functions like average or count. So I can just go ahead and now that I've grouped data, I can perform these aggregate operations on that group data. So this is working on multiple rows rather than working on a single row. So now I've got this grouping, and I count, and I use show this time to just print out what you'll see in Apache Spark. This is the ASCII formatted table here. And so we know that there's true for having a redirect is actually 3,600 of our entries, whereas false is 43. So there's actually a lot of articles that are referenced here that are just redirecting to something else. So that's something we'll probably just clear out because the text for those isn't going to be as interesting for doing our analysis. So here we're going to do a filter based on titles that had a parse error in them, whether or not redirect titles null, and then if the text doesn't have any values to it, we'll also just say like, okay, there's nothing useful information here, it's really just a stub article, let's get rid of that. And we can see what that leaves us with for articles. So we'll run that, we get 4,300 articles that we can operate on going forward. All right, and then, so here we have some Some of the helpful functions which I've been going through the API, that's where if you look at the Python or Scala SQL APIs, you'll see your group data, your column, your data frame, and then all the functions associated with those. And there's also the functions package or module, and that's what we're going to import right here. And we're importing it with an alias because there are some things in there that, just in case you would have a namespace clash because it has the same name as something else in your variables, you don't want to necessarily overwrite those. If you know it's safe, you could just import the various names that you need to use and use those directly. So we'll pull those in, and then we'll use a Python function dir, which just gives you all of the elements, all the attributes and methods on an object. And you can see that this is quite an extensive list. So let's go down here. We can just scroll through here. So you see there's some math functions like absolute value or cosine, dealing with arrays, a bunch of date functions in here as well. And if you go to the API, you can see the reference for all of this. There's like 100+ functions of very useful things. Now, the thing to note is you could write some of this stuff using your own functions, doing a user-defined function. But the problem with that is that, let's say you write your user-defined function in Python. Now it has to go out and run that UDF in the Python process, whereas these have been optimized and actually generate code in the back end, which is really fast. So to the extent that your function exists within here, or the functionality is close, it's really useful to use this to keep this running very fast and very optimal. OK, so we had a timestamp that we found within our data frame. Let's go ahead and take a look at that. We can see some of the values that it takes on here. This is really in a UTC format, but it's just a string, which we saw from our schema. So let's say we want to go ahead and convert that to a different time zone or to a different type. We can use some of those functions that we just encountered from the functions library and excuse me, operate on them. So the first one we'll use is the date format. So here we have func.date format. We could have just imported it and called date format as well. This is operating on a column, the column timestamp, and we specify a format here. Now what we're going to do is we're going to specify this format and then also rename it to something useful. We'll just call it the date. And we can show the first 5 of that. So let's see what happens. So now we get back our dates, and these do seem to correspond to the timestamps themselves. Now this function itself is not returning a timestamp or a date type or anything like that. It's actually just returning another string, and it can be operated on that string again. So it will work with strings. And we can see that by running the print schema. Here I'm using a different operation that you haven't seen yet. This is with column. So let's say we want to just append another column onto our data frame. A very easy way to do that is to use with columns. You specify the name for that column, and then use a function, use something that takes a column or just returns a column. So as long as you get another column into that next field, it'll work fine. And then you can go ahead and look at the schema, which is what we're going to do, and then select out some examples. So let's go ahead and run that. So we'll see the schema here actually shows that the timestamp was a string. The date coming back is a string, so we haven't converted types at all, but we do have a useful date. OK, let's see if we can do something a little more extensive than that. So now we want to do this timestamp manipulation to actually get back the time zone that's appropriate for what we're looking at. And since we're here in Amsterdam, we'll go ahead and use Europe Amsterdam. And this is going to create a new column, CES time, using this function. So this is just from UTC timestamp, something we could look up in the list of date time functions within this module. And then go ahead and run it. So we'll do a print schema after we do this. And that'll tell us what this schema also looks like. Now, nothing's really happened again here until we go and do this show operation. This is an action. So select is a transformation, but show is the action which will cause this execution to occur within the Spark engine. So we'll go ahead and select. Here I'm selecting also just the 2 columns out I want to look at, so just like a normal kind of SQL select statement. Let's run that. So we get CES time is now actually a timestamp object. It's still nullable. And we can compare, and we can see that we had this UTC time here. Now it's been adjusted to be appropriate for our time zone. And you'll see it actually is taking into account the different times for when it's a year difference from UTC, for an hour difference from UTC to 2 hours based on like your daylight savings time concept. So this is working nicely. Now one more thing we'll do is we'll use a lower function. So there's just a lot of functions that you'll find within this library that are useful for doing things you would want to do to pre-process your text, or whatever do your math operations if you have numeric variables. So here we'll do one thing that's a little bit different. We're actually going to select star, so you can see we can use this SQL notation. So instead of doing with column, I just selected star, and then I added another column to it as well. And I give it an alias for it being lower. So let's just take the first item there, and look, it has lowered it. It's very straightforward here. Nice operations to use. So what columns are left over? This point, so we've appended a couple of things here. We've got CES time and lower text. These are all part of our data frame now. Now that we have those in there, we really don't need all these fields. So we're going to use the drop command on a data frame to go ahead and get rid of a couple of these things, and then rename the one lowered text just to text, because that's what we're going to use to generate a list of words going forward. We'll run this cell. So we can see what fields we have now. These are our columns. And then just an example of what that looks like. All right. So here we're going to go into a lot more detail of how the ML transformers and estimators and pipelines and all of that work later. But we are actually using one right now. And we're just going to use it as it is. You can see that we set a couple of fields on it. The input column is corresponding to the column in the data frame that we're going to use. And then the output column is just going to be called words, because we're going to split this based on a regular expression that we provide. And don't worry about the regular expression. It's just saying, anything that's not a word character, if there's a bunch of those in a row, we'll split each side of that into an actual word that looks like a word that we might typically see. So we'll run that through, and then we'll call transform on it on the parsed data frame. And that'll return us a new data frame. Still, nothing has actually happened here. This is all lazy evaluation, so we've just created a plan for this. But now when we go out and take something from it, we can take the first words, which is an array of words that came back for that text of the article. And there's going to be an array of words for every different article. And we see some of these words are not that useful. They're really short, or they're stop words like the. So we're probably going to do additional work here to clean this up. All right, so what we'll do first here is to take a UDF that there is a stop words removal within Scala, but there's some additional stuff we want to do and specify here, and Python doesn't implement that yet. So we'll go ahead and create this UDF that'll do the work for us. If we look at the stop words remover within the Scala API, it has a list of words that it's using. So we can actually just put that list of words in an available S3 bucket, so we can build it from that list of words. And we'll create that by using sc text file. That's just loading in from this text file the list of words. There's going to be each element within the RDD is going to be one of the rows of words. We'll collect that to the driver, so that's going to bring all that data back. You're not going to want to do this for a large file, because you're going to bring everything back across the network to one machine where it might not even fit into memory, and that's going to cause a problem. But this is a small file. We just wanted to load it in parallel and get it to our driver. So let's see what's in there. I'm just going to take a look at the first 5. So we can see there's just some pretty common words that occur here. All right, now how would we create a function for removing these words? So the first thing we're going to do is actually create a broadcast variable. So all you need to know about a broadcast variable for this purpose is that you access it using .value. And we can create it with the Spark context .broadcast. So we took this array of words and created into a broadcast variable, which will be sent to all of the workers, and the executors will have access to that broadcast variable. And by using .value, we'll actually access the information that was stored in there. So it'll be the array of the words. Now this is an efficient way of actually sending information out. And if we're going to use this list multiple times across lots of different tasks, it's a very efficient way of moving that data set over to live on all of the executors. So we've created it as a set, and actually not an array, so that we can do a fast lookup. So they'll just make, when we search for a word, it'll be very quick. So this is just a very kind of long-winded function created to make it very explicit. If the length of the word is going to be less than 3, so just very short words, we're just going to get rid of those. So that's just returning false. We're going to use a filter on this shortly. So here, this is where we're using our broadcast variable. We use .value, so that's going to give us back the set. And we can use that on the driver or on the executors, and it'll still give us those same values. Once you've created a broadcast variable, it's usually a good idea to not change the underlying variables or try and change anything because you want to keep things in sync. So stick with the immutable mindset. If you're going to create a new one, I'd give it a new name, just so you're not running into issues where you've got a different version on your different executors, because you could get some very confusing bugs that way. OK, so let's go ahead and also check for anything that contains numbers or an underscore. It's just a regular expression that's going to look for that. If those exist, we're not going to keep those words either. And then we'll just wrap this function with another function that'll go through a list of words and decide whether or not to keep them. So we can go ahead and do this. This is just defining the functions and creating the broadcast variable. Give this a second. All right. And then we'll go ahead and test this function locally. So this is kind of interesting, right? This is a function we're going to wrap up into a UDF, and it's going to be available on the executors. We can also just run it locally on an array and see if this is working the way we'd expect. You can see that it's getting rid of anything with numbers in it, and then stop words like the, and then checking for the underscore as well. So we've cleaned up our list of words here a little bit. Now, how do we turn this into a UDF? And now, user-defined function is something where you've written your own function that can operate on the data frame column and do something useful. So we're going to import from functions UDF, and that's going to be used to create the UDF. But we also need to know what types we're working with. So that'll allow Spark with the core, the DataFrame API, to understand what types it needs to be working with for Scala. And here we're going to use an array type of strings. So we need the array type and the string type, and we pass in string to the array. So now we can tell it, what's this function return? It returns an array of strings. It's an array of words. All right, so to create the UDF, we can just use UDF, pass in the function that we created and tested, and that'll return us back the UDF. Now, another thing that's actually pretty neat about what you can do with UDFs is you can register them so that you can access them in a SQL-like fashion. Once they're registered, you can call SQL commands on them. So we're actually going to register remove words with the shift enter here. And it's a good idea that you, as we proceed through here, you're going to want to run all of the cells in the notebooks in a very linear fashion, starting at the top and moving through. Because once we get to exercises or other aspects of it, if you haven't run the earlier cells, you're not going to be able to do the next bit of work. And then this function will actually we'll call from another notebook, because this will register it with our SQL context. And then we can call this from, actually we could call this using SQL in a Scala notebook. And even though we've registered this function in Python, it'll go out and create the Python process, run this function within it, and we can kind of interoperate between things that way. And we will use this in a later notebook, so you should really get it into your SQL context. All right, so now let's go ahead and apply this to the words data frame. So here you can see we're using the with column again. We're just adding no stop words. We're going to drop it and then rename it into words just to keep the words as our name for our column. And we're going to select and take a look at what we have. So here we have we're taking just the first two lists of words that come back. And we can see that we don't have numbers anymore in here. And there aren't really stop words. There are some words that do occur frequently still. We might deal with that later as well. All right, so here we're not actually going to do this because you don't have write access to the bucket that we're using. But what I did when creating these was to go ahead and I've done all this work. Now I'm just going to save it down as a Parquet file, which I can load into another notebook, or I can work somewhere else, and I've got this saved state. I don't have to redo all this processing. And it's just a simple, you use write.parquet, give it a file name that's accessible. And that's going to be accessible to all of the executors that are going to write out that. All right, so what is this data frame actually doing? Well, there is a logical plan. Let's see if I can get in here. And as you can see, it's fairly complicated, the number of steps we've given it here. A lot of projections and going out to the actual file, the Parquet file, the small wiki that we loaded at the start. That's sort of where everything begins. And there's a logical plan that's created here tries to optimize it. This is where your Catalyst optimizer will go through and say, we've got all these different parts that we're doing this projection, but I have a bunch of rules that I know how I can collapse those things together. So I can do that to reduce the number of steps that actually have to occur and make this more efficient, possibly even reorder things if that's going to work. But then I have this idea of like, OK, this is the optimal way to do it logically. Now, what do I do based on where things actually are and create a physical plan, which will have my RDDs that can go out and do these operations for me. So here we see a tungsten project. But Project Tungsten is a big effort to actually be more efficient about memory usage and to avoid garbage collection issues. And it's turned on by default in Spark 1.5. And you'll see that it can help really speed things up and reduce pressure on the GC for larger amounts of data. And that's because things are stored within a binary format. And that binary format doesn't need to incur all the same overheads that you'd have of serializing and deserializing Java objects. So it's really a big push to make things a lot more efficient, and it will continue to be worked on and will really just kind of help make the process a lot faster and keep things working without dealing with these big Java overheads. All right, let's see. OK, so we'll go ahead and cache this because this is something we're going to operate on a few times. Once again, this is storing it into memory. If you wanted to take this out of being cached, you'd actually run the unpersist command. Now, unpersist really caches an alias for persist with memory only. So it's specifying that we want to just store this in memory. We could also store it in a serialized fashion or allow it to be stored in memory and on disk. There's a couple other settings as well documented in the API. OK, so now we want to calculate the number of words that are actually in our no stop words data frame here. OK, so we'll notice that it has, I don't want to skip ahead here. I'll give you too much information. All right, so this will actually be a section that you guys are going to work on. There's a few parts to this now. So if you have the notebook up, you should have the student version, so you shouldn't see the solution. But if you want to reference the solution, it's in the _answers notebook. And I'll just point out one way to look at the UI here. If we look at ML, so here I have mine under the MLlabs. And one issue you can run into is that, well, my screen is a little big right now, so I'll just shrink that back down to a regular size. There is a bar about halfway down. So if you can see that, it allows me to change the size of columns. So sometimes the names get a little bit long and they can be difficult to read. So we can just slide things over with that. Now the _answers you can see here, and _student. So I'd start from the student one, whichever language you prefer. Make sure you've run all the cells up to the point where there's a fill in. And then we're going to try and work through just solving the next few exercises. So I'll give you guys a little bit of time to dig in there and see if you can solve them, and then we'll work through them. I'll explain how they work. But go ahead and dig into that and start working on it. And we'll be wandering around to help out with any questions that you have on it. Yeah, so your first exercise is just to find the size of each of these arrays. And so you can see in the, for example, the Python API, if we go into functions, we can look up, just doing a search here, size to see how size would operate. Now, after doing the size portion, we're going to do, there is a test in here too to just make sure that it'll work. In Scala, there's an assertion, and if that assertion fails, you haven't passed the test. We're also doing something equivalent in Python, and it'll print out the message if it's not working properly. Otherwise, it'll say test passed. After you do the size, there's going to be one about actually aggregating up those counts. So we just sum up the size that we've specified. And then we'll do this in a different way using explode. And finally, we'll do a more extensive group by to see words, group by the actual words. So like, what's the account of how often this word occurs? Okay. I'll leave up the size reference here. All right, I'm going to go ahead and walk through how we can do these various exercises, and that'll give you guys a chance to take a break after this, and we'll have a 15-minute break where you can get some coffee or use the restrooms. So this first one here, we want to apply this function size, and that will allow us to get the length of the array for each of the rows. So notice I'm just adding in the column using a with column, size, this func that we've aliased from functions to call the size function, passing in the column words. And then you may have had, I think some of the Scala notebooks were actually missing the words. So we should be selecting out 2 columns here. And that will give us a row with these 2 columns so that the test can check the length of that first list of words that comes back along with the size that we've specified in our operation on the data frame. Now, in order to aggregate these sizes that we've created, we've got this sized data frame. So we can call ag on that. So this gives us an aggregation. It's doing a group by and then .ag in the background. It's sort of alias to that itself. And we pass in an aggregate function, which is sum in this case. So we just want to sum up that size column, which we generated in the prior step, and then give that an alias. We'll call that alias number of words. So we've just named that column that we created. Go ahead and do that. Actually, I didn't run this. Okay, so this first one I'm getting 681. And this should go through the entire data frame to sum up everything. So this will take a little bit longer. And then we've got a test that just checks to make sure that it is the number of words that we verified from before. And while that runs, I'll explain what's going on with explode as well. So in this section, we want to just use the explode function. And the explode function takes in an array and actually creates, each one of the elements in the array becomes a new row itself. So that'll allow us to expand it from being in this array here to an actual separate row. And then we can just take a count on that number of rows because those rows each row will correspond to one word. And I'm just giving that an alias here for word again. We'll run our count. We should get the same value back. Let's see if this completed. Uh-oh. You're having a Wi-Fi issue on this one. All right, and then finally, what we want to do is we actually want to go ahead and group by word itself to create an aggregate list. And here, I've got it broken up into a group, aggregate, and a sort step. And now the group by occurs on the word itself. So we do a group by on word. Now the words, whatever, let's say that it's ref, that's occurring. We now have ref and effectively all of the times that it's occurred. and we can say just calculate a count on that. And that's using this function count. We pass in word as the column again. And then we give it an alias for count, so we're just giving it a rename. And then we can sort that. Here we're using function descending so that we get the most frequent ones first. And then we'll just take the first 5 of those to take a look at it. Let me see if OK, cool. So this one reran now. All right, so we can see that the most common is ref, followed by user, HTTP. You see some of these look more like stop words in the context of Wikipedia. They look more like HTTP or HTML or some sort of reference as opposed to words that are occurring in articles naturally. So these things will actually, there's an exercise later where we'll pull out some of these words as well as an additional stop word removal. So then what we can do is we can register a temp table taking this wordless data frame that we just created. Now what that'll do is that'll allow us to actually use SQL to query this table, this data frame. And this could be queried from this notebook or from a Scala notebook, and it's as long as we have access to the same SQL context. If the cluster restarts, there's nothing persisted here. We're not saving this to the Hive metastore, which is where you would probably save your tables if you're using a Hive SQL context, which is the way that Databricks does work. But here, if you restarted your cluster, this table is gone. It's just ephemeral. It's really a link to the underlying RDD operations and whatnot that we're doing. So register that. And this will be specific to your cluster as well. So if you're working with multiple people on the same cluster, you could be overriding each other's tables as well. But that's why everyone has their own cluster to work from. We can go ahead and run just regular SQL. We're getting back the same result here. So if you're more comfortable in SQL, you can always do these data frame operations from a SQL standpoint. And we can call our own custom function that we created, our UDF that we did before, remove words within this actual SQL as well. So we've been able to extend the SQL functionality. And then within the Databricks notebooks, you also get this %SQL, which indicates that this cell is going to be a SQL cell. And I can run it and just write it in plain text rather than calling out to the SQL context itself. So we see, once again, getting the same values. Just to demonstrate something simple again, we'll take the word list and calculate out the distinct values for it. We're operating at the data frame level here, so it's just a call to distinct. So it'll do distinct because we only have a word in the one word per as a column. So it'll actually do it for words. And we'll take the 5, just get an idea of some of the words that are occurring within here. And how many are distinct words that we're going to be working with going forward. And so we've got like 118,000 words from not all that many articles. So you see there's quite a lot of variation within the text of Wikipedia here. All right, so it's 10:30 now. We'll actually do a 15-minute break. If people want to get a coffee, you can continue to work on the lab. I suggest that you actually at least take at least 5 minutes to stretch your legs and walk around, get away from the computers, because we've got a lot of material to cover. There'll be lunch at 12 as well, just so you can plan around that, and one more break this afternoon, probably around 2:30. So go ahead and take about 15 minutes, and then we'll jump back into some other stuff. We'll be covering machine learning with ML and MLlib next. There have been a few questions about what the availability of the notebook environment and the shards will be. So this will actually be up for 3 weeks, the DS01 through 06. You'll be able to log in. Right now, you all have your own individual clusters with a couple of nodes. That'll actually be changed to community clusters, so you'll just attach to the community cluster after tonight. Excuse me. But you'll have availability to log in and view the notebooks for the next 3 weeks. You can also export those notebooks to an IPython format or download those, and you can always do a trial of Databricks and upload a DBC file back with the notebooks in them and try and do some more analysis using that environment. All right, so next we're going to go through Actually, I'll show you real quick to make it easier. So if we have a notebook here, this top left bar, the 3 bars again, where we get to navigation. First off, you should all be working from your own folder. So make sure you find your email address in here or the student name that you're working under. And then like for here, I'm looking at my notebooks. Like if I look at this one, there's actually, it should be a labs folder in there. If you don't have a labs folder within your notebook, definitely raise your hand and get a TA to help you out with getting that over there. You can clone the existing labs notebook that exists at the root level into your area, but you should be working out of here. And if you wanted to take this entire folder and save it down, you could actually do an export as a DBC archive. Or you can, that would actually save it so you could use it on Databricks later with a different shard. But instead of doing that, you might want to actually look at an individual notebook. And you can click on the little down arrow here and do, I'll have to shrink it. You can do an export there as well to a source file or HTML if you just want to view it offline. There's a couple different options for how you can look at these. And I think for Python versions, you should see an actual IPython export as well. Yep, so you can go to an IPython notebook that you could operate in an IPython environment locally or however you want to do it. Okay. All right, so we'll jump into ML and the MLlib libraries next. All right. Okay, so ML is the newest library for machine learning built on top of DataFrames and uses some of the existing MLlib functionality. Sometimes things have been rewritten mostly from the ground up for some of the particular algorithms. But the real difference here is we're working with DataFrames, taking a DataFrame in as input, adding to columns, and then outputting. So like at the end, we might have a new column that says predictions. And along the way, we've done a bunch of transformations, and we could see the interim transformations where we've parsed the data into a format that works for machine learning. So they're used as the input to many of the operations. This is DataFrames are used as input to ML operations. It's a very versatile storage environment, so it has various types that we can use and a schema we can specify. While doing that at the same time, we can use this display and the show functionality to go ahead and see this in a very logical way. So now instead of like MLlib, you actually would have an RDD that you would pass into a library. And when you do that, you would just pass in like a dense vector that would contain the features that you want to use. And when you do that, you get back, you can actually get back like a model that you can make predictions on an existing RDD, but that'll just give you an RDD of predictions, which you have to then combine back together with the first thing through zipping the two things together. Here we'll just get a new column, and we can look at any of our observations at a row level and see what features we have, what the process was of how we got from one feature to the next, and then take that and see what the prediction is. There's not any like recombining things together, and it makes it a lot nicer. And then that output is typically going to have an additional column appended. Some things like you do logistic regression, you'll get multiple columns where you have a raw score, a probability, an actual prediction as well. So it's all of this extra information that you get in a nice package. All right, so there's some building blocks to the ML library. And then within this, you've got transformers and estimators as two of the major things. So the first thing we're going to discuss is the transformer itself. Now, a transformer is a class that takes one data frame and it produces another data frame. Now, the useful thing about these is it's really like, okay, I want to calculate the norm of my vectors, and I can take this in and then pass it out, and I can chain these together, which we'll see later in pipelines. And some examples of this would be like a hashing term frequency. So there you're just counting up the number of times that words occur, but you're hashing them to buckets, and you can specify how many buckets you want. And that can, the great thing about a hashing term frequency is it doesn't have to parse all of the data first. So you have some scheme for how many buckets you want to put things into. It gets the first bit of data, and it can just hash that and give it an index to where it's going to go. So it doesn't have to build up a model or anything like that. And also, you can specify how many features you want. So if you're just looking at words, but you only want a vector that has 10,000 features, you can specify, I want 10,000 Whereas if you did word counts, like with a count vectorizer, you'd actually have to build up a whole dictionary of vocabulary, and you could have maybe 100,000 plus terms. If you didn't want that many in your vector, this is one way to accomplish that while still retaining most of the information. Now, a couple other examples are like a bucketizer or a logistic regression model. So here you actually have a model that comes out of a logistic regression estimator. So you'll see this pattern quite a lot, where one model is created from an estimator, and then that model itself is a transformer, and that transformer can be used to then transform, in this case, for logistic regression, we'd be taking our inputs, our dense vectors or our sparse vectors, and converting those into predictions, the raw columns, other fields. And then also another example is the pipeline model. So we'll see pipelines, and you'll actually call a fit on a pipeline, and you'll get back a pipeline model itself, which is a transformer. So you'll find that everything pretty much goes back to transformers and estimators within ML. So the thing that a transformer does is implements this transform function, and that takes in a data frame and typically appends another column to that data frame. And it also, behind the scenes, has information about how to transform the schema that exists in the data frame. That's not something that you need to worry about. You're not going to be calling that function. That's more internal. So let's go on to estimators here. Now, estimators take data frames and produce transformers. So here you're going to have more examples of the actual machine learning models, but other stuff that you might not necessarily think is an estimator, because you'll see it under feature extraction and transformer sort of category. So examples of this would be, you're building a model, random forest classifier. That's going to produce a random forest model that comes out of it, and that model is going to be a transformer where we can make predictions. But the classifier that actually contains the information about like how do we actually go and train this thing and produce a model is going to be an estimator. Now, we'll see cross-validator used as well. That's really an estimator. IDF, so this is inverse document frequency. Now, if you do your term hashing and you have a bunch of different terms and you want to go ahead and say, OK, across all the documents, I want to see how frequently these things occur so I can weight them, and this would kind of correct for stop words automatically. A model has to be built up first that understands what are all the different words that are occurring and how frequently are they occurring across my set of documents before I can start to calculate IDF. It's kind of a global model. So that has to be built within this estimator framework. We return back a model, and that model can be used to actually transform our data. So we can take the output from the hashing TF and then create IDF values from it. Another example is our standard scaler or the pipeline itself. So an interesting thing to note here is that pipelines are estimators. They also take in estimators and transformers. So a pipeline can actually reference another pipeline as part of its stages. So you can get this sort of nested structure where if you've done all this work ETLing out and doing EDA, and let's say you've created a k-means model, and from that model you predict a bunch of clusters, you could actually put that as the first part of your new pipeline, and now this cluster could be part of your features for doing a supervised learning technique. It's kind of interesting the way you can just combine these things together because they're based from these estimator and transformer classes. So estimators are going to implement fit, and that fit is going to produce back a transformer. And once you call the fit, you'll get back a model that comes from it. So that'll cause some execution. So now with pipelines, we have pipeline. This is going to be an estimator like we just talked about, and it has various stages to it. And this is going to be a reusable workflow. So where this naturally makes a lot of sense is where you're doing the same operation multiple times. And a good example of that is a test and a train split. So we've split our data into testing cases and into training cases. And we'll train using fit on the pipeline, the training data. And that'll build us up a model where it's necessary, where we have estimators within the pipeline. Those will be turned into transformers. Those transformers will now be part of a pipeline model. And that pipeline model we can call transform. And it'll take in our, say, test information, so our test data frame. And that test data frame will run through each of those transform steps. It's not going to rebuild the model on the transformer on the test set because we've already got that model built based on what we did with the fitting of the pipeline, which is called the fit on the estimators. So the nice thing about that is we don't want to recreate our model, but we want to reuse all of the transformation steps that got us from the type of data we were starting with to what we can use to generate our predictions. And this example here, we can see that we have the DSO, that actually corresponds to a data frame going in, being split up into words or being tokenized in some way to create another data frame. So here's hashing as well. The tokenizer and hashing TF, those are both going to be your transformers. And then here we have the resulting DS2, which is going to go into a logistic regression model. So now that what we're doing there is we're actually calling logistic regression as a estimator. So that has to build a model. And that model is going to come back here as this LR model that you're seeing. And so the estimator, once we've returned back what this pipeline model is, it no longer is going to be part of that. It's now it's been translated into a transformer. So the estimator itself doesn't have to be rerun when we're running this pipeline.transform, or on the pipeline model.transform. And then we can use that to get this final output. There's a couple of stages to how this is working. Okay, so we're going to go through some of the features that are implemented in both ML and MLlib. So as far as estimators go, you can see that MLlib has your IDF, word to vec. There's a bunch of stuff in here. A lot more you're going to see within ML because you're really working with a data frame and how do you translate that by appending a column. So all the natural things you would want to do. A lot of this stuff would have been done in MLlib more by just taking an RDD and performing that transformation yourself. Well, these have been packaged up into very useful transformers and estimators that exist within the ML functionality. So these are all models. These will all return back some sort of model, some sort of transformer that actually then we would use to go ahead and transform the data from one thing to the next or make the predictions or whatnot. So now what do we have on the transformer side? You can see that PCA and SVD, it's really, under MLlib, it's implemented under, you're using a distributed matrix, and you can run these calculations there. This is just existing in the normal transformer way within ML. And then other examples like we just covered was the hashing term frequency or a normalizer, et cetera. So some additional ones. There's quite a bit more of these in ML, so we can really see those all listed here. And things that are useful for just combining together your features like a vector assembler. Like you had two actual double variables, and you want to make them into a dense vector that you can use or a sparse vector that you can use for your training. You actually just use a vector assembler to put those two things together. And then now that could be your features column that's input to your next part of your model. All right, so how about in the clustering world? There's a bunch of unsupervised algorithms here for clustering things. And you'll find that there's, on the ML side, not a lot has been ported over yet, but there is k-means. On the MLlib, you still have a lot of these other models. And if something doesn't exist within the ML world, you can just go back to the RDD from your data frame. So you take your data frame, convert it into a type that'll work for these MLlib libraries, and then you call the MLlib library on it, and you'll have to do some things typically with like zipping up your output and whatnot. But more and more of this is going to be coming in the next versions where all this stuff will start to get ported over. All right, so classification and regression, kind of more your typical workhorses of supervised learning where you're trying to train a model and then make your predictions. You see here there's pretty good coverage across both. Now, it's not necessarily that the implementations are not exactly the same. In some cases, things are very similar. In other cases, they can diverge a little bit, like logistic regression is being done a little bit differently between MLlib and MLlib. You actually call just what type you want to use. So you're saying, I want to do logistic regression, but I want to use stochastic gradient descent, or I want to use LBFGS. Within ML, you actually you can specify a mixed parameter for your L1 and L2 regularization, and it's working to try and solve that problem instead. And it actually, like logistic regression doesn't support multiple classes within ML at this point, but you can do that in MLlib. But that stuff's all coming. There's also another way to do it in ML with the way things exist now. I have a couple links in here too, just so we can go to the documentation. Again, let's see here. So this would be your programming guide for MLlib, and then you go into the linear methods. As you can see, there's a lot of really good information about what's actually going on with like logistic regression. You've got the formulas, you've got information about multinomial logistic regression, how it's working, what they recommend. There's 2 algorithms to solve it, gradient descent and LBFGS. If you can, LBFGS usually converges faster, so that's the recommended way. You'll see other details like that. And there's just a lot of links and information within here. So definitely search around. And this is the MLlib section of things, but there's also going to be references within the ML documentation. So we can pull up linear methods for ML, and we'll see here, we're starting to talk about elastic net hybrid L1, L2 regularization. You can still just set your regularization parameters to 0 and get the same result of not using it. Or you can specify I want all L1 or L2. But it adds this different kind of functionality in. So it's good to take a look at both documents and see just what you want to really use. All right, let's go back. All right, and so you see coverage is pretty similar between the 2 of them here. And then there's also collaborative filtering and frequent pattern mining, but the frequent pattern mining hasn't been ported over to ML at this point. And then evaluation. So evaluation is, okay, we've built a model. This is really going to be under the supervised guys. And when we build our model here, we want to know, okay, how good is this model? So you could just go ahead and actually try and calculate your accuracies or your precision and recalls. But there are evaluators that are built in that can do this for you. And so it makes it very easy to just specify what parameter you want. So I want to know area under the rock curve as my parameter. And I can go ahead and create a binary classification evaluator and then use that to get just what that value is. I can also use in ML, I'll use these evaluators to tell cross-validation just what it should be evaluating for tuning my parameter search. So definitely want to use these. See, there's not multi-label or ranking metrics that haven't been moved over at this point, but you've got all of the major workhorses within binary classification, multi-class, and regression. All right, so from here, we're going to jump into some labs, and we're going to explain more of how this works. You're going to see how it all works in detail through the lab exercises. So let's go back to the Databricks environment. And then you'll find this one will be under, make sure you're, again, working within your own username directory, and then it should be under the labs folder. And then the first one we're going to do is 1, which is the MLlib data types. So we'll see that the data types are used across both ML and MLlib. There are some that are used more specifically for MLlib, and then they're packaged up into data frames for ML. But it's good to really understand the vectors that exist, because you're typically going to have features that are existing either in a sparse vector or a dense vector, and that's what's used to train our models. So we'll go ahead and go into this directory. Again, we have Python and Scala versions and student and answered. There's a few exercises in this one too, so I recommend you go with the student version here. And if at any point you are getting stuck or feel like you're getting behind, raise your hand, and the TAs will come out and help out with what they can. All right, we'll go ahead and load this. Uh-oh. That's not good. Give it a second. I think I need to refresh. All right, I'll try and make it a little bigger. So, is that pretty good again for people to see in the back? Well, I guess more in the middle, because you're probably the furthest, actually. Just raise a hand if you can see this clearly enough to read the text, or, yeah. Maybe I'll go a little bit bigger. Okay, great. All right, so the idea here is to really learn what data types we're going to be using typically in these models. And the key ones are the dense vector and the sparse vector. If you're using MLlib, you're going to want to be using labeled points for when you're doing things like regression, or rating objects if you're doing alternating least squares and things like that. So again, the Shift-Enter to go ahead and run your cells here. Of course, make sure you attach to the cluster. So let's do that first. One thing that you can note too is you'll see if you hover between 2 cells, there's this large plus button that comes up. You can create new cells. So feel free to go ahead and and test out some stuff in there. If you want to do a take on a variable or get a better understanding of what's going on, you can write your own code in there, and then try not to alter the variables themselves to reset them, because then some of the later parts of the lab won't work. If you do have a problem there, you can go back and clone from the labs directory a file and start again, or just switch over to the answers version as well. All right. OK, so we'll do an import here from linear algebra and look at it. And we can actually see that this is where a lot of the different types live. So we have matrices, and we've got vector. I also see UDT. So this is something that goes right with the ML user-defined functions. If you want to actually return back a vector type, you would, or a matrix type, you specify this as vector UDT. Now, the rest of these actually live in Spark SQL types, but these just happen because they're ML specific to MLlibs and ML specific to live within the MLlib linear algebra. So definitely keep that in mind if you're looking for those. So we've got our sparse and our dense vectors. And I'm just going to go ahead and import some of these types to get us started here. Now, a dense vector is really just an array of values, and that allows us to store things like, let's say I've got 100 features, I can have an array that has 100 values to it. In Python, it actually uses, it delegates a lot of work out to the NumPy, and you can run NumPy type operations on your dense vectors, or call np dot whatever on your dense vectors, which is nice for doing some calculations locally and seeing what's going on. Now, dense vectors and sparse vectors do live locally. They're not distributed data structures in themselves, but as we make them parts of a row in a data frame, or we actually go ahead and put them in an RDD, then they're ending up being parallelized across the cluster, but each dense vector itself is going to be living on one particular node. There is a distributed matrix class. Most of the functionality is implemented in the Scala side, but not the Python side. But you can do things with that if you want to do distributed matrix operations. All right, so let's go ahead and, once again, I've got links here for the APIs. So if you want to look at the Python API for how MLlib data types do work, or the programming guide actually is pretty extensive on this. So I'm just going to bring that up real quick so you guys can take a quick look. And then let's see here. So this is the Spark programming guide. Link's not great. OK, MLlib. And then within here, we go to the first thing. It's data types. So you can see vector, label point, local matrix, the distributed. And there's lots of good information about just how these work within here. So a great reference. All right, and then you can always go to the source code. We haven't done this yet, but on GitHub, the source code for PySpark and for Scala versions of Spark are all right there. So you can go ahead and dig in and actually see what's going on under the hood if you're so inclined. So I think this is pretty small right now. But so we've got MLlib, and you can go into linear algebra and then see how things are actually going to be defined. All right, so jump out of there. All right. Once again, you can use help. Help's useful within Python to go ahead and get some information about just how these things work. So we'll start with a dense vector, and dense vectors do implement a couple of things. It's different a little bit between what's in Scala and what's in Python, but within Python you can call things like dot to get a dot product, or norm to calculate the norm of the vector, and you can multiply them together. You can't multiply them together in Scala. So first thing we'll do here is we'll create a dense vector, and we'll call it just dense vector with a lower d. And you'll note you're using the vectors object to do this, and it's a recommended way of doing it. You can also create it from a dense vector itself, but this is sort of like a factory method for creating these objects. And it'll go ahead and handle getting you the correct type. So I've actually passed in ints here in Python, but I'm getting back like a float or a double value. And it's always going to be stored as doubles within Spark. So we always get a vector that has double values, and then we can perform some operations on it, like doing a dot product. And that's just a mathematical summary of how that would work. So let's go ahead and do our dot product. That does work fine. In Scala, that's not implemented, but we can do norm in both languages. So norm is a good way of calculating a distance measure, and we'll be using the normalizer. So Euclidean norm is the most common, where we're using a power of 2. The technical details of it don't matter that much, but it's a good way to standardize on a row basis if we have a set of features, and we want to say, okay, I want to use a distance measure like k-means, I can normalize everything so that I can get more comparison across the absolute distances. So we'll do this using vectors.norm, so there's another way to call it rather than operating on the vector itself. And this is something we can call from Scala as well. And so I'm just specifying 2 for the L2 norm. So that means now the sum of the squares of each of my values in my array are going to sum to 1 if I've normalized this. So here we see it's not a normalized vector. All right, so within Python, it's pretty cool. You actually get this functionality where you can actually multiply things together element-wise or add in another value to your vectors. A little more difficult to do in the Scala side of things. But we can always, in both languages, get back out our values with a 2 array and operate on that array ourselves. So now we have our values back. And just to see what type that we're dealing with here, let's go ahead and take a look at that. And see here we have a NumPy ND array. So this is just it is really a one-dimensional array in this case, but you could have, this type for NumPy actually does classify out to multiple dimensions. So now sparse vector is the next thing we're really dealing with. And sparse vectors can be created just like we use vectors.dense, we can use vectors.sparse. Now, we'll specify for that the length of the sparse vector. So here we're saying we have a sparse vector that is 10 elements. But we're only going to specify elements. This is actually 0 index, so this is going to be elements 3 and 8. And we give values for those. So setting those to 1.0 and 5.0. So this allows us to store things much more compactly. And if you're using something like doing text analysis, you'll find you have very sparse features. So if you tried to create a dense vector, you'd just run out of memory. So it's a very useful tool. And we'll really just be going between vectors, dense vectors and sparse vectors for a lot of what we do with ML and MLlib. All right. So again, just some more information about the links to the APIs. You'll find that just having the APIs up all the time is super useful, and just go back and forth and read what's in there. And if you want, you can dig further into like the source code. But here we can use the dir just to list out all the methods that are on sparse vector. This is specific to Python. So, all right. So if we take a look, we can see. Anyway, we've got toArray, dot, norm, squared distance, various functions that are implemented in case we forgot and we just want a quick reference. And then this is actually on the object that was instantiated itself. So let's go back to how we did that. Here we created our object. First thing passed in, again, number of elements. These are indices to which elements we're setting, and these are the values we're setting them to. You can also pass in a dictionary. I think you can pass in tuples as well. There's a couple different ways to do this. But you get the same result out of it. Now, if I wanted to look and actually, with Python, you can compare and say, what's the difference between, it's kind of interesting. I've got a class here, and then I've got an instantiated object of the class. And some of the stuff that's happening is actually being done during the constructor phase. So there's these 3 fields that are being set for a sparse vector when an object is initiated. And I can see the difference between these 2 things by looking at what's actually implemented for those classes. So indices, size, and values are all set. And so if I wanted to actually pull out what the size was, or if I wanted to know the size of the number of elements that are actually set for this particular sparse vector, for this instance of it, I could say indices, give me the length of indices, because that's going to be, I've set like 3, in my case here, I set 3 values, I think, right? Or 2 values, I set 2 and 7, so it would tell me it's 2. Meanwhile, it has a length of 10, so I have a sparsity of 2 over 10. All right, so let's continue on here. Now we could say, using this Python functionality for inspect, I can go ahead and just get the source code actually as well. So it's kind of a neat way to just say, what is really going on here? Let's pull up the source code for PySpark. And you can't do that in Scala, but it's really nifty for PySpark to be able to jump in and say, what's going on? And OK, I got a parameter size. I've got these args that get passed in. Based on what comes in, I'm going to decide how to create the indices and the values. There's a bunch of different, based on the types that come in. Is it you're setting it to be a NumPy array with the int32 or a float 64 for the index versus the values? And you can just run through these codes and see what's actually implemented and how it's working. So really a lot of work is going out in Python's case to NumPy. All right. So let's take a look at some of the types that we're getting back as well for a sparse vector. So we can see that it's just looking in Python as though the size is an integer. The indices are an ND array, so a NumPy array. They're in 32-bit. and then the values are actually doubles, or floats, 64s for NumPy. So it's a good idea to not set these things specifically, because if you get the type wrong, sometimes you can screw things up where it's expecting one type and you've actually set it. That's why we'd want to use the dense vector, the vectors.dense or vectors.sparse to specify these things, because it avoids any of these type issues that you could run into. And just examples for within what you can do in Python. This next line isn't going to work because sparse vectors actually don't operate with a plus that's not been overloaded. So you have to do that more manually if you wanted to add them up, but typically you're just going to be allowing libraries to build off of these things. So within MLlib, the next thing we're going to talk about is the labeled point. Labeled point is typically what you use in your regression models, where you specify this is the label, or in your decision trees, things like that. So you have a label, and you also have a set of features. We can see again with help just what we're working with. And label and features are accessible as class attributes. So that's how .label, .features can pull those things out of a labeled point. It's not like a tuple or anything. You can't just index it with a 0 or a 1 to get the values back. So you want to use label and features to extract the values from it. All right. So how do we create one? So I'm passing in here a label, 1992, and then a bunch of features. So I've got 3 features here. Maybe they're song attributes, and this is the year we're trying to predict. So we can see also the classes we're getting back here. It's created for the features. It's automatically given me a dense vector, and the types actually float for the label, and it's also going to be a float or a double for the features within the array. So we can see, again, the set differences. We've got features and label. That's how we access these things. And I can do same thing here. I'm specifying a sparse vector this time. So label point just has a label, but then the next part, the features, is a vector. So I can store that as either a sparse or a dense vector. There we have that. So rating, now this is going to be used within like ALS, where you actually want to put together, say, a product and then ratings that were given to it, or say it's movies and I want to give a product ID and a user ID and how they were all rated together. So you can reference, again, help and then also the various APIs for this. And you can take a look at the source. So it's the same sort of way. We're just going to create one here. We've got value for user, value for product, and then a rating that goes along with both of those. And then within DataFrames, which is not really an MLlib data type, but it's very important for using ML. So we'll cover just a little bit of detail here on how we can create one of these using a named tuple. So that's a Python functionality. The equivalent thing really in Scala would be to use a case class. At least the closest thing. Because the name tuple here is going to work so that it can do the inference automatically on figuring out types and things like that. And it'll keep everything in order. So we can actually specify a name tuple like address using just specifying what these parameters we want to go in are. And it's going to be city and state here. And then I can see what my types and various things are. I've gone ahead and created, there's 2 ways to access things. We can use the dot notation or index in this case because we have a tuple underlying this object. And then I can create a data frame by operating on this. So here I'm getting a data frame with just a couple of entries. Okay. So now we can go ahead and create the named tuple. I'm doing this using label and features, which actually looks a lot like what we saw under the labeled point. So this is kind of more like how you'd actually represent a labeled point within the ML framework. Now I've got, instead of it being a labeled point object itself, I can pass into my learning algorithms something that's the label, and I say this column is the label, and this other column is the features. So I don't pass in a labeled point at this point anymore, but I've extracted those out into 2 separate columns, and I pass those in. All right, so we'll just do a couple of quick exercises here about how to create a dense vector, how to create a sparse vector, and I think I'll switch over. So if you guys want to go ahead and pull up this notebook and make sure you go to the student version of it, and then start working on these exercises, and we'll go around and check. After this, we'll actually start building some models and getting more into the pipelines and things like that. This, this part, because it should be pretty straightforward. It's really an API call, so if it's not something you're getting, it should be just something you should see and know how to use it. So all we have to do here to create the dense vector is call vectors.dense passing in an array. And we can verify that that's what was expected. Now, a labeled point takes in the label and then also an array, a vector, really. So here we're just going to reuse dense vector and specify that our label should be 10. So I've just called label point within this. We have to create a new object with, actually, I think it's got a constructor within Scala. So it should work fine in Scala the same way. And then we can test that that verified out. Oops. Close these messages. All right, and then the UDF, which we haven't really covered the details of how to do this. We've sort of shown you some stuff with UDFs under the Wikipedia lab. But what we can do is we can import this UDF from functions. That allows us to create a UDF. And then from types, we'll need to give it a return type. In this case, it's going to be a double within the Scala world. So we use a double type. And then the first element is just what we're naming this function to be. And the UDF, we pass in a vector in this case. So it's getting from the column, it's going to get a series of vectors. And we can just call bracket notation on that vector to get out the first value. So that first value will be returned. In this case, in Python, it's returned as a NumPy type, which is not something that is expected in the Scala world. So we convert that to a float, which is a basic type that the Scala side of things will handle just fine, and it's a type defined within SQL. So that'll work properly. So we'll just go ahead and call that on features and get our first element out. Again, we're using like an alias to rename this column, and we're using a user-defined function to take a column and turn it into another column. So we can see that the 1 and the 1.5 come out of this, and that was based on the first element of our feature array. Cool. We can just verify that. And this passes. So if you guys want to reference this, it's just right here. There's also in the answers notebook, you'll see this as well. Okay. All right, so next up, we're going to move on to the second lab in here. And this will be doing a little bit of ETL and moving into building an actual k-means model. So we'll do an unsupervised learning here. So this is under your labs folder, ETL k-means. And then there's the Python and Scala versions again. Under Python, this one's a little different. It actually has 3 parts to it. And this is just in case you get behind on a part and you can't get that part to work. I'd recommend what you do is you open the _student one, which has everything in it. Part 1 will only go through part 1. But if you take, let's say you don't get the answer to part 1, you can open up part 2, and that'll have the solution through part 1 and start you off at part 2. So you just make sure you run all the cells until you get to the part you're at. And that'll give you the proper setup for your notebook. And then you can continue working on the next part as we get to that. Or you can always go to the answers as well and just reference that. So go into here. OK, so now we're going to actually use a transformer and estimators and actually build out a k-means model with this lab. So first off, what we want to do is we want to load some data in. In this case, we're going to be using a tool that's added into the MLlib, just under ML utilities, to load in a SVM file. So this is a lib.svm format. And we could also be loading things in as a text file, or maybe we already have something in a data frame. Here, just an example of one way that we could load information in. Make sure we attach, of course, to our cluster. All right. Go out and read this data back. Now, this under the hood is actually, I think, using a text file read and then actually parsing the data to bring it back. And that's going to be done in parallel as well. I'm specifying here a minimum number of partitions just so that we can have this in a nice parallel fashion and see how that would actually be broken up if we broke this data set into 20 parts across our partitions on our workers and executors. So we're getting back a labeled point. So this is obviously built with the idea of using it for MLlib as opposed to ML, because we really move things into just labels and features when we're working with data frames on the ML side. But what's this format really look like? I can just pull this text file in using the Spark context.txt file and give it the path and take a look at the first 5 entries. So this does actually sparse vector storing. And we can see this third, which we're really working more with dense vector at this point because most of them all have values. But you can see that in this case, the second entry didn't have a value with it, so it's actually set to 0. So this will just be set to 0 if we ever converted it to a dense vector. All right, and then how does this data get stored as it gets loaded in? And now we've got all these partitions. We've got workers and executors. I've got now my 20 partitions, and I'm using some RDD functionality here, so don't worry about the exact details of this. But I can look to the partition level itself and get an index for that partition and then run an operation. So here I'm just telling you what's the length of this number of elements on this partition and return that back so I can inspect it. So the 0th partition, or the first partition, is going to have 8 elements. I have 7 on the next one, 8 again. And you can see it's been distributed out across, but it's a small data set for this example. But that allows us to see that it's not all residing in one spot. It's actually now we can be distributed across 20 machines. And if it's a much larger data set, we could be putting 1/20th of it in each of these machines approximately. OK, so let's go ahead and take this, and we actually want a data frame. Well, I could actually just call toDataFrame on it, but now I'm getting a sparse vector for features, and for a label, I have my label. So that's actually kind of cool. Like, I've had just an object here, and now it's been converted into a data frame that has the 2 parts that I wanted. So how did that actually work? Well, let's take a look at what we were working with again from here. So we've got our, it's just a repeat here, so let's skip that. So if we want to show it into another format, we can just display it here. One parameter you can pass to show is truncate. And then what we're doing here is we're actually extending out the column so that we can see all the information there. Sometimes it'll just cut out. So if we say don't truncate this, let's see all the information that's available. And then we'll go down, take a look at the data frame that we created. This is just using display. So we can see, again, the same information. This is a type 0 with size 4, so it has a size and also has an indices. So that's a sparse vector, because remember, those are the attributes we had on sparse vectors. And then we'll go from there down and take a look at the schema that we're working with. So it gave back us 2 types within this, 2 fields within the schema. And the first field is going to be a vector. So that's that vector UDT. Remember, that was defined under the MLlib linear algebra module. It's not under types within SQL, but this is where you'll find it if you ever need to explicitly use it. And then we also have a double type for the label. And we can see the schema in a kind of a nicer way as well with the print schema command. Oh, yeah. Here, keep this a little bit bigger. OK, so then if we want to see how this is actually working underneath the hood, we can go ahead and create a class that has a couple of attributes and then see what happens. So here I'm going to create a person object, and it's going to have a name and an age. And we'll just specify a data frame that's based on 2 of these people. So we'll go ahead and display that. We'll get an age and name, and we can see that seems to be working properly. So how is that actually working under the hood? And here we're going to dive into just a little bit of the source code real quick so that we can see if we want to figure out how something's happening, we can dive in at any point and figure out, oh, this is what's actually going on. So here I've got sort of the stack trace for what needs to be called to get to inferring the schema, because we haven't specified. We didn't give it a schema, so it has to go out and figure out what is actually underlying. So I'm going to jump through these first ones and just go right into infer schema where the real work's being done. But definitely feel free. These are all links to the GitHub source code, so you can review this in your own time and go into more detail. But let's bring this in. So here, we can see that under infer schema, where did it go? OK, cool. So what's the instance that's coming in this case? We could pass in a dictionary, and it would give us back tuples based on the items in the dictionary. So that would work for actually getting a schema out of the object. If it was a tuple or a list, we can use this way of doing things as well. For a row, we can actually take a look at the fields in it, or underscore fields for a named tuple. So we saw the example with the named tuple. So this is actually explicitly going out and figuring out how to get the fields out of these objects so that we can create a data frame from them. And then in our case, we actually, classes that are created the way that we did, in Python actually have a underscore underscore dictionary object. And that has, when you instantiated the object, it actually has the items within it. And so those are any of the attributes that we've set. And we can call items on it to get back a tuple of a list of tuples of the values, their names, and their values. And that's what we return back as items here. And then we loop through creating structured fields. Remember we had the structured type before and then structured fields within that. So we go through and create these structured fields. We're setting nullable to true. So it's just, by default, it's always going to be true when we create objects in this fashion. And we return that structure's type as our schema. So this is how Spark's doing some of the inference behind the scenes. And from here, let's move on. OK, so we can see from the object we did create, it does in fact have this underscore dictionary object, and this is what's in it. So you can see how it would work to go out and get that information and create the schema. And then we'll show the schema again that was created. So we have our structured fields. This is what was looped through and created. It all looks like makes sense from what the code we saw was. We could do the same for the name tuple. Seeing the same thing, it's working here as well. And we saw the code that loops through and does that too. So let's take a look at that schema. One thing to notice is the order has actually been changed. When doing it from an object, it just sorts out, and you get age first because it starts with A and name second. But we specify with a name tuple an actual order, and that order was retained. So if you care about that, you can always swap the orders by doing a select statement with your data frame later too. Now we can see our schema that was created. All right. Now, we actually have 3 different values within this for our target variable that was pulled in based on the way this data set was created. So one thing we might want to do is actually go ahead and say, let's zero index these, because that's what Spark expects, both in MLlib and ML. We need zero indexed targets. So we're going to use go ahead and, showing too much information. But what we're going to do is we're going to go ahead and create a UDF, not a UDF, we're actually just going to use a SQL expression to go ahead and subtract out a value, subtract 1, to bring these from being 1, 2, 3 down to 0, 1, 2. And then we can use those later on. So this is a part you should go ahead and pull up the notebook, try and work through this next section to get the answer. So following this one, there's also you'll actually create a UDF around doing the first 2 features, extracting the first 2 features. So go ahead and work on that as well. And then where you see part 2, that's where we're going to stop and go through these 2 exercises. So only go through those 2. And then if you do get stuck on this, you can always load the part 2 file, and that'll have solutions for these 2 things. But make sure you run all of the code up to where part 2 is before we start going through the next section. So I'm going to go ahead and go through these 2, and then we're going to go ahead and there's another exercise after this about k-means and building the estimator. So we'll get through this part, and then we'll introduce that and have a chance to work on that a little bit. And then at 12 o'clock, it's going to be time for the lunch break for an hour. So we'll just get through this portion, and then we'll break for lunch. OK, so how do we go about subtracting 1 from our column? So we can just select out the features, and then also a column where we can just use our mathematical operator, subtract, and the value 1. We're going to give that the alias label to rename it back to being a label. Let's go ahead and run that and see how that's working. We can see our labels are starting now at 0. So we need to call of label because when using the operator overloading that's built into the minus, it needs to know that it's working with a column. If I just used label, I'd be trying to subtract 1 from a string, and that's not going to work. You could also index your column using some of the other methods that we showed before, so whatever your preference for doing that is. An alias is just, again, to rename the column to whatever we want to call it. OK, let's just check that. And then now we're going to look at the UDF and how would we build a custom UDF here. So what we're doing here is we're actually creating a UDF where we're using a Lambda function. We could just create a separate function and pass that in as well, where it's a def or it's something we've defined and using that reference. But what I'm going to do is take the sparse vector and create it as an array. So now it's in a dense format, and I can pull out the first 2. Now, this was a really large vector. You probably wouldn't want to do it this way because you have to convert the whole thing to dense. But you could actually look at the first two elements and use an operation where you just index 0 and index 1. So you just have these two quick lookups and then package those into an array and return that. And since we're now have this array from doing this slice operation on it, the next thing we could do is we would actually go ahead and call vectors.dense. This is our thing that generates a dense vector. And we pass in an array as the parameter for it. And it's important in Python, we have to specify the vector user-defined type, because that's of type vector. Both sparse vectors and dense vectors would be able to be returned with this type. Now, within Scala, it's actually, the compiler can tell what types we're working with, so we don't have to specify the return type. It can infer it from the context. So let's do this. OK. Now, if you've had any trouble getting these or couldn't follow along to type in and get it to work with what I've shown on the screen right now, then go ahead and open up part 2 file for your particular language and run the cells using your Shift-Enter up until this point where you'll see part 2. And that'll get you in the exact same spot that I'm at. Okay. So here we can see what's this actually being represented as. OK, so the first element that's coming back is, in fact, a dense vector with our 2 values in it for what we wanted to get, the first 2 values out of our sparse vector of 4 values. So it seems like things were working properly. All right, now let's go ahead and view that. We can do it in 2 different ways. We could just do a take or we could even do show or display. So we'll go from there. And this is just showing that features is, in fact, the name of the column, and that it's a dense vector with these values. And then we also have labels as the other column, and there's your value. All right, so now that we have this data frame, we could go ahead and save this work that we've done down to a Parquet format, so we wouldn't have to recreate this, or maybe want to share it with a colleague, or just come back to it later and not run all the other steps we've already run. So I can use the write Parquet under the SQL context, which in this case I've got a data frame, so I can just call write Parquet, and then what I'm doing here is I'm generating temp files just so that we don't have a lot of collisions. We're going to create a random number, random UUID, and then write. So you can go ahead and see how that would actually work. And this will write a Parquet file format out and save the data in a reusable format that's really quick to load back in and continue our data analysis at some other point. And we'll use this file in some of our other, I'm writing out to a temp directory for now. I've already done this, and we have access to an S3 bucket with these values in it. And this is the only directory I think you guys have write access to at this point. So what does this Parquet file actually look like? All right, so let's go into here. And we can see we've got some metadata and information about that. But then we also have a part that goes with each of the different partitions we've broken this into. So we can continue scrolling through here. And we'll see they're gzipped, so there's actually compression being applied to these Parquet files. And we'll have 20 different Parquet parts. So those can be loaded in as separate files from S3 at 20 all at once from our different workers. If we get nice parallelism out of this, and it's a compressed, efficient columnar storage. OK. Now from here, we're going to go on to actually doing some k-means. So this will be our first real version of a machine learning algorithm. And this is going to be an estimator within the ML world. We'll also see how to call it from MLlib. And we'll take a data frame, translate that into RDDs, and call that at the end. So we've got details from what we saw before. We've got the estimators and transformers within the APIs. So we can look up details on those. Sometimes the APIs and the details aren't particularly detailed. So you'll want more information. And for that, I've given you a link to PCA and logistic regression, which are shown in the ML programming guide. So you can kind of see how different ways of setting your parameters for an estimator. And there are nice examples there. One thing we're going to do a little different from the examples is we're just going to set the values. Let's just scroll back here. So we're just going to set the values, and then we're going to go from there and then call fit. And then once we call fit, we'll get back a model, and so we'll break it up into a few more stages here. So go ahead and take a look at this example and start working on this. This will be the last thing we do before lunch, And then when we get back, I'll review how we go about actually doing this, and we'll continue on actually building out the k-means model, visualizing it, running it in MLlib as well. So go ahead and start working on this, and we'll come around and help if anyone has issues. All right, we're going to go ahead and go through just how you set this, and then we'll break for lunch, and we'll come back together in an hour at 1 o'clock. So here, I'm creating a k-means object, and then I'm setting the various parameters. Now, within Python, you can actually set these within the constructor too, but we'll follow the same syntax that you see in the Scala examples as well, and do our setting one on each line. And here I've wrapped k-means in parentheses so that I can just actually do these on multiple lines. You could also use a new line, a slash for a new line character, so that it knows that there's actually an extension of this onto the next line. So I'm just going to set k, which is the number of clusters I want. I'm doing a seed for reproducibility, so this is a random number generator. Max iterations, just to do 20. This actually converges pretty quickly for this data set, so there's no reason to let it go any further. This is something you could definitely change depending on your data set, see how things are iterating through. We'll use this to also see what the process is doing and how it converges as it moves on. And then init steps is the initialization steps for the k-means parallel algorithm. And I'm just going to set that to 1, because if I set it to too high of a value, I actually start moving too far on my getting to the right clusters. So it's just for demonstration purposes. You probably want to leave this at the default, or maybe you'll find for your data set you actually want to increase it or decrease it a little bit. Once I have a k-means object, I can just call fit on that. So that's an estimator, so we can call fit, passing in a data frame. This is iris2 features of the data frame we're working with. And now it knows you can set the column input and also set the column output. But what for the features and for the label. But the way in which we named our data frame has label and features, and those are actually the default values. So that'll just work for this case. In other cases, we'll actually specify exactly what we want to do. And then this is a k-means model that we get back under model. And from there, we can call cluster centers to find out where each of our clusters lives, and what's the mean point, the cluster center from which we're going to measure to decide whether or not something falls within that cluster versus another. And we'll see visualizations on this after lunch for just how this technique works if you're not familiar with k-means. Once we have a model, we can transform our data. So now the model is a transformer like we discussed. And this we can call transform on and pass in that same data frame again. And so we'll pass that data frame in, it'll do the transformation, and we'll get back what those actual predictions for which clusters we are, what we're in, looks like. And we can go ahead and run this. We'll print out just what the centers were so we can see we've got our 3 different, we set k to 3, so we have 3 clusteroid centers, and we'll have our 3 x and y values effectively here for when we do our plotting. And we're only using a 2-dimensional space in this case. I mean, you could easily have 10,000 or something like that, very much larger features. I'll just confirm that this works and it's passing through. And if we wanted to see, we'll just go ahead and add in another bit of code here. So this was now called transformed. So what do we get? We have a label and a prediction. And you can see that the label and the predictions are different, but it's just because we're predicting it into a cluster. So we actually just want them to be consistent. So if 0 usually maps to 1, or 1 usually maps to 2, that's actually a great thing. And it's kind of naturally clustering things based on what the labels were to begin with. But this is unsupervised. We haven't trained based on using the label information at all at this point. All right, so we'll come back and get started at part 3 after lunch. So we've got an hour to go ahead and break and go ahead and enjoy your lunch, and then we'll come back and get started again.